Well, it's great to have a chance to speak here. Those of you at the mini meeting have already heard plenty about the octonions, so I'm afraid you may think that I'm only interested in the octonions. I'm actually interested in many other things. The octonions are just completely a hobby for me. I'm mainly these days working on the foundations of mathematical biology using categories, in fact. So, I could have given a talk about something very different, but somehow I was in the mood for having a chance to explain lots of different aspects of the octonions to the same group of people, so that some of you may decide you hate the octonions and never want to learn about them again, but others may learn about them and realize how beautiful they are, and this is sort of a good way to learn a lot of stuff about them. So this is a project I did with my graduate student, John Huerta, and also my he's a former graduate student, and my other former graduate student, James Dolan, and a good friend of ours, Geoffrey Dixon, who actually works in web design. He helped create some of the animations in this talk. They're fairly simple animations. I'm sure he can do much fancier things, but he's also very interested in the octonions, and so that's why I was able to persuade him to create these animations. So Felix Klein, when he got his habilitation in Germany, had to give a speech. That's what you had to do when you get this degree that's after the PhD in Germany, especially in the old system. And so he wrote a speech for getting this job in Erlangen, or getting this position in Erlangen, and it was called the Erlangen program, and he actually never gave that speech, but nonetheless it was very influential. He also didn't like Erlangen, and he left Erlangen fairly soon after that, and eventually wound up in Göttingen. But the idea of this program was to use group theory to systematize geometry. So at the time, geometry did not mean differential geometry like Riemannian geometry. It meant different forms of axiomatic geometry, the classic one being Euclidean geometry, but then at this time in the 1800s, there were beginning to be many other forms of geometry. So one of the most important at the time were I'll list a few. First, of course, the discovery of non-Euclidean geometries. So the hyperbolic geometry and the spherical geometry were realized to be just as interesting as Euclidean geometry, and they all fit into a kind of family where you can vary the curvature and go from the negatively curved to the flat to the positively curved case. But also very important was projective geometry, where you have no notion of distance and angle. It's a much simpler form of geometry where you only have a concepts like point, line, plane, and the concept of a point lying on a line, or a line lying on a plane, and you write down axioms just using that vocabulary. And then you can then you can also work analytically on such geometry, that is using numbers to study it, but you can also work synthetically, axiomatically. And what Klein noticed was that each of these different kinds of geometry had a symmetry group that was fundamental to that geometry. It's just the symmetry of the space that you're working on. And the various types of geometrical figures, like points, lines, and planes, were related to various subgroups of the symmetry group. So if you have a group which is acting transitively on some space, for example, the Euclidean group acts transitively on the set of lines, then you can think of the set of lines as a quotient of that group by the stabilizer group of any line. And so the geometrical figure line is associated to that particular subgroup of the symmetry group. So what Klein realized is that a type of geometry is a group, and then once you pick a group, there are different types of geometrical figures, and they are just the subgroups of that group. And then you can go on and you can understand relations between geometrical figures in this way. So for example, when you have points and lines, the most important question is, does the point lie on a line? And you can tell whether a point lies on a line by studying the stabilizer group of the point and the stabilizer group of the line and seeing how they interact. And they interact in a very different way depending on whether the point lies on the line or not. I don't think I'll go into too much detail, but it's really good to understand, and somehow it's never quite been written up in enough textbooks, this Klein approach, which we can now do very beautifully, better than he could, because we have a whole bunch more mathematics available to us, like group theory and category theory, that allow us to formalize that. One direction things went at this time was that Sophus Lie invented the concept of Lie group, and then later on, Killing and then Cartan classified the simple Lie groups, and Coxeter much later and Dinkin before that realized that associated to simple Lie groups, which are the sort of best behaved Lie groups, there are certain diagrams called Dinkin diagrams. So, for example, if you're doing three-dimensional projective geometry, the symmetry group is SL4, the transformations of a four-dimensional vector space. You could do SL4R if you want to study real projective geometry, or you could do SL4C if you want to do complex geometry. But the Dinkin diagram is sort of able to handle all possible fields you might use for your geometry. And there will be a Dinkin diagram associated to this simple Lie group that doesn't depend on the field. And the Dinkin diagram for SL4 is just this picture here. It has 3 dots and 2 edges. Now, if you've studied Lie algebras, that's where you would be most likely to meet Dinkin diagrams. And they'll tell you some other story about what a Dinkin diagram means. And that story is also true, and it's completely compatible with this story. So you may hear some story about a maximal torus and roots and weights. It's an extremely technical sounding subject. I hated it at first because I didn't understand why I should care about all these things. Now I understand why you should care about them, and part of why I understand that is because there's a good attitude where you think of the dots in your Dinkin diagram as different types of geometrical figure in your geometry. And you think of your edges in your Dinkin diagram as invariant relations between geometrical figures. So a point can lie on a line can lie on a plane, and those relations are invariant under the action of the symmetries. In case you're wondering how this is related to anything you ever heard about Dinkin diagrams, you may have heard that the different dots in the Dinkin diagram correspond to so-called maximal parabolic subgroups of your Lie group. And those subgroups are the stabilizer groups of these types of figure. But that's actually rather technical, and really that's not the right way to start the subject. The right way to start the subject is just to say, if I'm doing three-dimensional geometry, I've got points, lines, and planes, and a point can lie on a line, and a line can lie on a plane, and so I should draw this little picture and start from there. So one can do it that way, and it's compatible with the more common approach. So there are 3 different connected Dinkin diagrams that have 2 dots. There's also one that has 2 dots and no edges, but I won't talk about that one. So these Dinkin diagrams have mysterious names, A2, B2, and G2. The 2 just means there are 2 dots. But what you can tell from what I said is that these are describing different kinds of geometry, and these are geometries which have one thing in common, that they have two kinds of figure. So this one might have points and lines. And what about these others? Well, it's probably good to always call them points and lines, but they behave differently. So the geometry for the A2 Dinkin diagram is projective plane geometry. It's one dimension down from the projective three-dimensional geometry on my first slide. So the symmetry group of the projective plane is basically SL3, or you might say PSL3 if you want to show off. But the axiomatic idea of a projective plane is that you have a set of points and you have a set of lines, and then you have an axiom that says any two distinct points lie on a unique line, and any pair of distinct lines intersects in a unique point. So you have got points, lines, this relationship of lying on, and this is sort of a picture you should have in your mind for what projective plane geometry is like. Some people would consider this picture here to be too small or too degenerate to count as a projective plane. So some people want there to be more points in an official projective plane, but this is in some sense the most fundamental projective plane. So it has some points, some lines, and it obeys this axiom. And to understand the other two Dinkin diagrams that I showed you, we just need to take this picture and change it a little bit. So B2 is a geometry that has points and lines, but it's no longer true that every pair of points lies on a line. So the simple picture of a B2 geometry is this. So here we have some points that are connected by a line, but there are other pairs of points that are not. However, it always takes at most two lines to get from one point to another. So if you live in Manhattan, where the streets form a grid, right, you can get from any corner to any other corner, in theory, by going along two streets. So that would be a similar type of situation. So that's I'm not giving you the full description of B2 geometry, but that's the main idea. And these two edges here, the reason why there are two lines there is because it takes two to get from one point to another. And there's a group that's the symmetry group of this particular geometry. It's the symmetry group SO5. You should probably think of it as SO5C to get it to work out best, because sometimes things don't work so well over the reals without a little extra fussing because the reals are not algebraically closed. So if you study Lie algebras and Lie groups, you'll be able to start with this Dinkin diagram, build the Lie group SO5, build two subgroups, which are the stabilizers of the point and the line, and see how everything I said falls out. Then there's G2. So G2 is similar. Now there are three edges here, and that's because now it takes at most three lines to get from any one point to another. And that's the geometry I really want to talk about, because while the other two groups that I described have nice familiar descriptions in terms of matrices, so SO5 is 5 by 5 matrices that are orthogonal with determinant 1 and so on. G2 doesn't have such a nice simple matrix description, so it's a mystery, a bit more of a mystery. It's called an exceptional Lie group, and it's the smallest exceptional Lie group. And so if you ever want to try to tackle exceptional Lie groups, this is the one to start with. So the way that usually is considered the best for understanding G2 is you say that it's the symmetry group of the octonions, a certain non-associative algebra. That's fairly mysterious sounding in itself, of course, because normally they don't teach us about non-associative algebras. So it sounds like a fairly exotic thing to start thinking about. That is the simplest description of G2, probably. But I became very happy when I started reading a number of papers, some written by people here even, who saw that G2 is also the symmetries of something that's very easy to explain by comparison, which is, well, you'll see later on it becomes a little more complicated than I'm making it sound, but it's basically just the problem of a ball rolling on another ball in ordinary three-dimensional space. So you can make up a kind of geometry where the points are the ways that one ball touches another ball. So this, and also the orientation of, so let's call this like this, a big ball that we hold fixed, and then there's this little ball that moves around. So a point would be a place of contact where the little ball touches the big ball. But also there are different ways you could turn this little ball around and still have it touch at the same point. So those would all count as different points. So they're just ways that the one ball can be, the small ball can be located. And then the lines are just the ways that the small ball can roll along a geodesic or a great circle without slipping or twisting. So it rolls as if it's like made of rubber and it's touching something else made of rubber. So it doesn't skid or twist around. It just rolls in the most nice way. And so you can talk about a point lying on a line. If we have this motion here, that would be a line, and this is one of the points lying on that line. And if you set this up correctly, this will obey the axioms of G2 geometry. So this is the first time I'd ever seen anything about exceptional Lie groups connected to such a simple problem of the sort you might see in some kind of physics class, classical mechanics class. However, it's tricky. You need to get three things right to make G2 appear. So now you'll see that it's actually a little subtle. So first of all, the small ball, the rolling ball, it's not exactly an ordinary ball. It's a spinor ball. So what does that mean? Well, a while back, physicists discovered something amazing about nature, which is that there are particles, like electrons, protons, and neutrons, that if you turn them 360 degrees, they don't come back to where they were. They're different. And it took people a lot of time to understand that. Now we understand it. We say, well, it's because the rotation group is not simply connected, and it has this double cover, SU2. I don't know if that means we understand it, or we just like no fancier words to explain it, but nonetheless, it's true that if you turn an electron around 360 degrees, it's different. But if you turn it around 720 degrees, then it gets back to where it started from. So this rolling ball, we have to treat it as being spinorial. Only after it's turned 720 degrees do we count it as being back to the way it was. On the other hand, this big ball, this fixed ball, should be funny in a different way. It should be not really, so the surface of this big ball, it shouldn't really be a sphere. It should be a projective plane. In other words, to be touching at some point of this big ball counts as exactly the same as touching at the antipodal point. So the little ball only needs to roll halfway around the big ball for it to count as touching at the same point. So you'll notice there are factors of 2 involved in both of these, but they're acting in opposite directions. So the little ball, you need to turn it around twice as much as you'd normally expect for its orientation, I don't know the right word for it besides orientation, for it to come back to the same position as it was, but it only needs to go halfway around the big ball to count as touching at the same point. So those are both rather strange but important things. And now the really strange thing is that this is only going to work if the big ball is 3 times the radius of the small ball, or else the other way around, but then of course you wouldn't call it a big ball, right? So So we'll just work with the case where the big one is 3 times smaller than the small one. So when people discovered this through calculations that go back all the way to Cartan, who started having this idea that G2 was related to rolling objects, but then worked out in more detail by Gilbert and Richard Montgomery and Robert Bryant and lots of other people, and me and my friends. The big question was, what's so great about the number 3? Why does it work just then? So there's an answer to that. Okay, so here's a little ball that's rolling on a big ball that's 3 times as big. And if you pay careful attention, and I may need to repeat the movie so that you can, you'll see that when it goes all the way around, it turns around 4 times. So it's a very good puzzle to ask people, just like take 2 coins of the same size. So in the United States, the best coin for that would be a quarter, because so I don't know what the best Mexican coin for this is. It needs to be big, and it needs to have something like someone's face on it or something, so you can tell which way it's pointing up very easily. And so if you take a coin and roll it around the other coin, how many times does the guy's face turn around? Someone answer. 2 equal-sized coins. I'm an American. I'm sorry. I'm going to use a quarter. This is very imperialistic. Okay, so for me, it's George Washington up there, right? So how many times does George Washington? I'm sorry, I didn't prepare to figure out who's the corresponding person in this culture. So how many times does George Washington's face turn around during this process? 2, not 1, but 2. So if you don't believe me, get some coins and check that out. Here's another question that's related. So let's say that there are 365 days in a year. Okay, actually there are 365.252 So, but let's say that there are, I'm talking about astronomy, not politics or what people decide to call. But so let's say that in terms of the sun going around the Earth, there are 365 days in a year. So then there's a question, how many times does the Earth turn around its axis each year? So in other words, you wait a year and you look at the stars in the distance, which are relatively static. How many times will you see them go around you in a year? So you see, it's a little bit of a tricky question because the Earth is turning around, but it's also going around the sun. So does anyone know how many times the Earth turns around each year? Well, think about, what was the question about George Washington? So you had equal-sized things. It goes around. Your naive guess might be that it would turn around once. So your corrected guess was, no, it goes around twice. So now you did the right thing, but you went correction in the wrong way. So he said, no, it's not 365, it's 364. No, sorry, it's 366. So there are 365. So we'll work it out. Think about it. So these are very fun things to think about. They're very simple geometry, but it's a great way to annoy your friends. You can ask them these kind of puzzles. So in particular, if you have that this radius is 3 times equal to that, then as the little one goes around, now watch it, 1, 2, 3, 4, right? So it turns around 4 times. So the reason why it's good to have the little ball be 1/3 as big as the big ball is not because there's something wonderful about the number 3. It's because there's something wonderful about the number 4. If you have this situation, by the time this ball gets all the way down here, it will be touching at the same location as it started with. Because remember, we count it touching here as the same as touching here. But also, it will have turned around twice. Because going all the way around, it turns around 4 times. By the time it gets here, it will turn around twice. So by the time it gets down here, it will be in the same location on this projective plane. And because it's spinorial, it will also be in the same orientation. And so that's the magic that makes certain things happen. Only for this ratio of radii. So amazingly, the symmetry group of this situation now, where we have this concept of point and line given by positions of the ball and ways for the ball to roll, is a G2 geometry, a symmetry group that's the same as, well, I'll correct that in a minute, but basically the same as the symmetry group of the octonions, which sounds like a very exotic algebraic entity. And in fact, you can get the octonions by starting with this rolling ball problem and doing some process to it called geometrical quantization and building some vector spaces which turn out to be the octonions. But instead of doing that, I'll go the other way, which is much simpler to describe. So what I'll do is I'll start with the octonions and get the rolling ball from them. But now I have to correct what I said. I've been talking in my lectures about the plain old octonions. Now, if you thought that wasn't bad enough, I'm going to talk about the split octonions. I'll give a completely self-contained and also different presentation. So you can define complex numbers as pairs of real numbers where you multiply them in some funny way. This formula looks a little bit weird because we normally don't talk about the conjugate of a real number. So you don't need the bars, really, in this. But the nice thing about this formula is that this formula for multiplying pairs, you can reuse it. So, of course, we also define conjugation for complex numbers to be reversing the imaginary part and keeping the real part the same. So here, in this example of the complex numbers, a bar is equal to a. But why I want the bars in these formulas is because once you know what the complex numbers are, you can define quaternions to be pairs of complex numbers where you multiply them using this same formula. And now you really need the bars because you use the complex conjugate there. And then you can go on again, and you can define octonions to be pairs of quaternions where you again multiply them by this same formula. And these are the 4 normed division algebras built up in a systematic doubling method. Each one is twice as big as the previous one. So in each case, you wind up getting a quadratic form that's positive definite, namely just x times x bar, which you know very well for complex numbers, and it works the same for these other cases. And it has the property that it's positive definite, and it's also multiplicative. So this is the q of x you can think of as the norm squared, or absolute value squared of x. And this is the nice relationship between the norm and multiplication that's the definition of a normed division algebra. And it turns out that this is how you get all 4 normed division algebras. And then the really amazing thing is that if you try doing this process again, you get a 16-dimensional algebra, but it's not a normed division algebra anymore. The machine breaks after 4 uses, and there's no money-back guarantee. So you can also do something where you just change the formula a little bit. I should probably go back because I'm sure you didn't remember this formula. So this formula had a minus sign in it. If you change that to a plus sign, that's the only difference, you can define what are called split algebras. So if we start with the quaternions, for example, and we give them this other way of multiplying, we get something called the split octonions, O prime, and we can define conjugation the same way, and we can define this quadratic form, x times x bar, the same way. And this quadratic form will still get along with multiplication in this manner. But now it's not positive definite anymore because we stuck this we switched the signs in some silly way. And And so now, if you think about it, do a little calculation, you'll see it's a quadratic form that's non-degenerate but indefinite. It has signature 4, comma 4, because if you work out, if AB is some pair of quaternions, and you multiply it by its conjugate, and see what you get AA bar minus BB bar. So you have 4-dimensional space of the first quaternion that gives you something positive definite, but then the other 4-dimensional space gives you something negative definite. So that's why it's called split. It's split between being positive definite and negative definite. So the automorphism group, the symmetry group of the ordinary octonions is the compact real form of the exceptional Lie group G2. But the automorphism group of this split octonions is another real form of the Lie group called the split real form. So it has the same dimension, but it's different. It's not compact. So I'll call this G2 prime. So G2 prime is, of course, going to act on O prime because it's the symmetry group of O prime. So it has this 8-dimensional representation, but of course it will, because it's acting as automorphisms, it will preserve the identity, and it will preserve the 7-dimensional space of octonions, of split octonions that are at right angles to the identity. So those are the purely imaginary split octonions, IM-O prime. So remember, an octonion, we're thinking of it now as a pair of quaternions. So if we demand that it be orthogonal to 1, there can't be any real part here. So we just have this 7-dimensional space like this. And here I, j, and k are the usual basis of the imaginary quaternions. And these coefficients here are all real numbers. So there's this 7-dimensional space of imaginary split octonions. And the group G2 prime has a representation on that. Because it acts as automorphisms, it preserves the quadratic form, which we've constructed from the structure we had around. And this quadratic form on IM-O prime will have signature 3, comma 4, because we left out one of the 4 guys here, right? We left out the multiple of 1. So it will have 3 positive directions and 4 negative directions. So when you have a situation where you have a quadratic form that's not positive definite, it's very nice to look at the set of vectors for which the quadratic form is 0. And in physics, that's called the light cone, because we happen to live in this universe with 3 space directions and 1 time direction. And the right quadratic form for us looks something like t squared minus x squared minus y squared minus z squared. That's what Einstein discovered, that you have to improve Pythagoras by sticking time into the Pythagorean formula, but it gets a different sign than the space directions. And so light spreads out at the speed of light, and so if you have a burst of light, it will spread out in this expanding sphere, which is really a cone in 4 dimensions, and that's just the cone of vectors for which this quadratic form vanishes. So it's called the light cone. So that, in this universe that we're talking about here, it's a weird universe where we have, say, 3 time directions and 4 space directions, 4 space dimensions. So that this funny space-time is 7-dimensional. The light cone, because one equation is being imposed, will be 6-dimensional. And then it turns out to be very nice to projectivize the light cone, that is to decree 2 vectors to be equivalent if one of them is a real multiple of the other. That will be a projective variety, an algebraic variety, and that will be 5-dimensional. Now, that's where the G2 geometry really lives. So, to repeat, this projectivized light cone, you should think of it as the space of light rays, lines through the origin that are sort of, whose space component is equal in size to their time component. This is a picture where we have like 2 space directions and 1 time direction. I couldn't really fit on the slide the picture where we have 3 time directions and 4 space directions, but it's the same idea, right? And math is always about, like, you imagine something in 3 dimensions and you pretend you're imagining something in 7 dimensions, and people think you're a genius, right? But you just do calculations to make sure you don't screw up. So in our geometry of the projectivized light cone, each of these light rays will count as a point in this geometry. Now, if you have a vector in this light cone, so remember, this is a pair of quaternions where this is purely imaginary, and that's a general quaternion. And we know that their lengths must be equal for the pair to lie in the light cone. We can always normalize it so their lengths are both equal to 1, or their lengths squareds are both equal to 1. So A will be a unit imaginary quaternion, so a point in the 2-sphere. Right, there's a 3-dimensional space of imaginary quaternions. While B is just any old unit quaternion, so it will be a point on the 3-sphere. In fact, you can think of the unit quaternions, because they're closed under multiplication, as a group, and it's just the group SU2, which is a 3-sphere. So the projectivized light cone will consist of pairs like this, a guy in S2 times a guy in SU2, but we've gotten rid of some of the rescaling freedom by imposing this normalization condition, but not all of it, because we could still multiply A and B both by -1, and they would still obey this normalization condition. So we have to mod out by that equivalence relation to account for the fact that we're projectivizing. So that's one way to think of this G2 geometry. But there's a really nice thing that happens, which is that although it's defined, although we've picked this equivalence relation here, this space, the projectivized light cone, is diffeomorphic in a very nice way to the space where we mod it out by a different equivalence relation, where we say that AB is equivalent to minus AB. So we only stick a minus sign on the first, in front of the first guy. So in other words, what we're doing is we're saying take points in S2 cross SU2, but the first point counts as the same as if we negate it. So what we do is we're just taking S2 and identifying antipodal points, so we're turning it into the projective plane, RP2. So this projectivized light cone, where the geometry lives, you can think of it as being RP2 times SU2. But if you remember, that's what we were talking about a while back. This RP2 cross SU2 is exactly the space of possible ways for a spinorial ball to sit on a projective plane. Because the orientation of an ordinary ball, by orientation I mean like the way you've rotated it. It's not quite a perfect word for that in mathematics, but I could take it and rotate it in lots of different ways. For an ordinary ball, the set of possible ways would just be identified with the rotation group SO3. But for a spinorial ball, you have to use the double cover of SO3, which is SU2. So that's this SU2 here. And that's why you need to rotate a spinorial ball twice around any axis to get it back to where it started from, because SU2 is a double cover of SO3. Now, for a ball rolling on a sphere, its point of contact will just be a point on the sphere. But now we're going to use the projective plane, RP2. That's the sphere with antipodal points identified. So a ball rolling on the projective plane is just a ball on the sphere, where we say that if you roll it halfway around the sphere, its point of contact counts as being the same. One way you could imagine that is you could have like two small balls rolling on a big one. And so then once they've gone halfway around, as long as you can't tell which one is which, you're back to where you started from. So that's the space, PC. But what are the lines in this? Well, there are two ways you could try to define the lines. So one is you could use the rolling ball method. You could say a line is just a path that's traced out as the rolling ball rolls along a great circle without slipping or twisting. So that concept of line will actually depend on the ratio of the radii of the two balls, right? Because how the small ball moves as it goes around the big one will depend a lot on their radii, but only on the ratio of the two radii. So let R be this ratio of the radii. So that's the way I describe lines first. But there's another way, an algebraic way. you can define lines using the split octonions, which I'll explain later. And then a theorem, which I'll make more precise later, is that these two concepts of line will agree with each other if one ball is 3 times as big as the other, and only then. So it's only then that the split octonions get connected to the rolling ball problem. So let me be a little more precise about that. So remember what this projectivized light cone, PC, is. A point in PC is a light ray that is a collection of vectors that are all multiples of the same vector on which the quadratic form vanishes. So it's a one-dimensional subspace on which the quadratic form vanishes. So one of these rays in this cone. So that concept of point, you'll notice, it doesn't really use the multiplication of the split octonions. It's sort of overly grandiose to bring in the split octonions there, because all we really need to know is what is this quadratic form on this 7-dimensional vector space to make sense of this previous sentence here. However, we're going to use the split octonions more significantly to define lines in PC. And one way to do that is to redefine points in a more fancy-sounding way. So we could define a point to be a one-dimensional null subalgebra of the octonions. So it's a one-dimensional subspace on which the octonion multiplication vanishes. So for the ordinary octonions, they're a norm division algebra. So you're not going to find any one-dimensional subspaces on which the multiplication vanishes. But here we have this quadratic form of signature 3, 4, or a signature 4, 4 on the original split octonions. So funny things can happen. And in particular, there can be subalgebras on which the product just completely vanishes. And then you can define a line in PC to be a collection of one-dimensional null subalgebras, all of which lie in some two-dimensional null subalgebra. So there actually are two-dimensional subspaces of O prime that are closed under multiplication, but also on which the product completely vanishes. So those will be our lines, and of course, it's easy to understand what a point lying on a line means. It just means that the one-dimensional subalgebra is contained in a two-dimensional subalgebra. So this is where things get sort of tricky, because we're really using facts about multiplication of split octonions. And so the precise version of that theorem that I mentioned is that if and only if r is equal to 3 or a third, that's the ratio of radii, the following two concepts of line are the same. So the first one is a line is a path or a set of points in PC traced out by this spinorial ball of radius r rolling without slipping or twisting along a geodesic in the projective plane that arises from the sphere of radius 1. So this is all about rolling balls. And then the other one is that it's a collection of all one-dimensional null subalgebras of the split octonions that lie in some particular two-dimensional null subalgebra. So in those cases, these match. And it's a kind of calculation to check that those match. And I wrote a paper with John Huerta where we do that and try to make it as clean and simple as possible. So in these two cases then, we have this, well, in these cases, r equals 3 or a third, then we can talk about the group of transformations of PC that map lines to lines, line-preserving transformations, and that will be this symmetry group G2 prime, this non-compact form of G2. So the question is, can you actually use this to visualize situations where you have to move along 3 different lines to get from one point to another? So remember, I said the feature of a G2 geometry is that you have points and lines, but there's not a line between any pair of points. to get from one point to a generic other point, in fact, you will have to go along one line and then stop, take a break, get some gas, and then go on another line, and then take another little break, and then go on another line. So it's like, you can imagine some country where you can get from any town to any other town by traveling along 3 highways. So can you actually see that that's true if a line means the path of a ball rolling on another ball, that you can't get from it one orientation to and point of contact to another by a single line, by a single rolling along a geodesic, but you need 3. And yes, there's a very nice example of one where you need 3. It's harder to prove that you need 3 without doing a bit of calculation, but it's sort of easy to see that 3 is a natural way to do it. Sorry. So let me just, before we get going, so here's the big ball, here's the small ball. This little black thing is to help you see the orientation of the small ball. So if it started turning around this way, this black line would start moving around. As this small ball starts moving, it will change color. And the reason why is because it's a spinorial ball, so it has the funny property that by the time it turns around 360 degrees, it's not back to where it was. But how do you draw that? How do you draw something that when you turn it around 360 degrees, it looks different? Well, that's where the magic of animation comes in handy. You just have it change color. So the color will depend on the amount of rotation. So we'll roll down to the equator. You'll notice that, right, remember when the small ball rolls around the big one, when it goes all the way around, it turns 4 times. So here it's gone 1/4 of a circle, so it's turned around once. So in some sense, it's back to where it was, but once is not good enough for a spinorial ball. So that's why it's turned green, okay? So you can see, hey, it's not back to where it was, it looks green now. That's how electrons work too. If you turn them around once, they turn green. It would be much simpler if it were that easy. Okay, so that's the first step in the journey. And then the second step goes around the equator. And now, notice it's gone back to its original color because it's made another 360-degree turn. So now it's back to the same orientation that it had initially, but of course it doesn't have the same point of contact. So it's not back, well, so anyway, so that's where it is now. And then with the third roll, it rolls down to the bottom, to the South Pole. And now, because the North Pole and the South Pole are antipodal, it has the same point of contact, but unfortunately it's green, right? So that it's not back to the same orientation. So what we've done is we've gone through 3 journeys, through 3 stages of a journey, and we haven't gotten back to where we started from. So we started here, moved along one line, moved along another line, moved along another line, and we've gotten to here. Sorry to suddenly decide to use chalk. I hadn't really been planning to. So you can prove that to get from this point to this point, you really need to use 3 lines. And then, of course, if you wanted to keep traveling around the world, like, okay, we've gone that far, you could keep on going, and you could get around back to where you started from using 6 stages. And so you would, in terms of your motion, you would have started here, go down to the equator, then go over to here, then go down to here, then go back up to here, then go around the equator, and then go up here. So you notice those 6 points are the corners of an octahedron. So there's actually a deep relationship between G2 and the octahedron. If some of you are like fans of exceptional Lie groups, or Lie algebras in general, you'll know something about like the weight diagram of G2, and you'll see that like when they talk about G2, you see some picture that looks like this. They don't tell you what that picture really secretly is it's part of a picture of an octahedron that's been squashed down to the plane. And this octahedron that's hiding here is the same as that octahedron. So there's lots of fun stuff going on. I guess you could turn off the lights. Well, I can't. Okay, I'll just show it to you once more, okay? Much faster. So bling. Now it's green. Now it's back to where it was. Now it's green again. So that's the rolling ball geometry. So to prove that this actually works, I've made a lot of claims here without any proof. I'm not really going to give a proof. You'll be probably relieved to know because the proof is a little bit complicated, but there are ideas in the proof that are very nice. So one basic idea is that the dot product and cross product on R3 really come from thinking of, you can obtain them by thinking of R3 as the imaginary quaternions and using quaternion multiplication. So this is how Hamilton did things before this evil fellow Gibbs invented the dot product and cross product. So for Hamilton, the cross product was just the commutator of imaginary quaternions divided by 2. And the dot product was the anti-commutator multiplied by -1/2. So these formulas for the dot product and cross product on R3 also work if you use imaginary octonions, and then you get a dot product and cross product on R7 that obey many of the same axioms as the usual dot product and cross product. And it also works if you use the split octonions. So if you use the imaginary split octonions, which remember is a space, 7-dimensional space with signature 3 plus signs and 4 minus signs, that has a dot product and a cross product on it, given by these formulas here, where you use octonion multiplication. And it turns out that you can define the split form of G2 as the group of linear transformations that preserve both the dot product and the cross product. So this is very nice stuff. If we all lived in 7 dimensions, everyone would learn this in college. But we learned 3 dimensions, so we do the 3-dimensional version of the same thing. And then it turns out that the concepts have been talking about all have very nice descriptions in that language. So a point in the projective light cone, remember what that means. It's a 1-dimensional subspace of the imaginary split octonions that is spanned by an imaginary split octonion where the quadratic form vanishes. Well, that quadratic form really just comes from the dot product. It's x dot x. So there'll be some vectors whose dot product with themselves vanish, and any one of them will span one of these light-like rays, that is a point in the projectivized light cone. And then you can ask, when is it true that 2 points in PC are at most 1 roll away, meaning you can get from one to the other by moving along a single line? And it turns out that that's true if and only if their cross product vanishes. So now in ordinary 3-dimensional geometry, right, if you have 2 vectors whose cross product vanishes, they have to be pointing in the same direction. But here in this 7-dimensional a funny signature case, there's more ways that the cross product can vanish. So there will be lots of y whose cross product with x will vanish. And then 2 points will be at most 2 rolls away if and only if their dot product vanishes. So in fact, in particular, it turns out that the cross product vanishing implies that the dot product vanishes. So the most strong condition is that x is equal to y, and then the next condition is that their cross product vanishes, and then the next weaker condition is that their dot product vanishes. But a typical point, a generic point, an open dense set of points can only be obtained from X by 3 lines, and then no equation, no such equation holds. So these are the ideas that connect the concept of the rolling motions to the algebra of the imaginary split octonions. You have to prove these things, but they're just calculations. So that's basically the story. And I want to mention that it's really quite a long story. So starting out with Wilhelm Killing discovering this 14-dimensional Lie algebra when he was trying to classify simple Lie algebras, Killing got a little excited and he didn't do the classification exactly correct. Cartan came along and did it perfectly. And Cartan did a lot of amazing things. And in this article by Robert Bryant, it's a good introduction to some of the work on Cartan, who related things like G2 to the concept of a motion of something rolling on another thing. But back then, a lot of Lie theory was done locally. They didn't have the concept of a manifold. So they were doing things locally in coordinate charts. So the global aspects of rolling motions weren't incorporated in Cartan's original work. There are various papers, and I see I've left out some important ones that make me very embarrassed. I don't know why I left out the one by Bohr and Montgomery. That's incredibly embarrassing. All of which are different people's treatments of trying to understand the relationship between G2 and the rolling ball. And in particular, Bohr and Montgomery give a nice argument for why the ratio of radii should equal 3, but they weren't satisfied with their argument. That is, with its, I mean, it was correct, but it didn't make them happy enough. And so that's why James Dolan and I, and then John Huerta, started working on it a bit further. And so I guess you could say our contribution mainly was just the realization that the reason why it's nice to have a ball be 1/3 as big as another ball is because then it will turn around 4 times when it rolls around. And that is what makes this nice magic occur involving the projective plane and the spinner. So we were reasonably happy with that. So I think that the octonions will slowly be found to have important uses, limited but important uses in problems in 3-dimensional geometry. And this is one example, and we're starting to see some more. And so I hope that continues, and I hope that gradually over time the octonions will become a little bit less mysterious than they always have been. Thanks.